In this lesson, we will focus on Task 3.2, Case 1 within Project 3, which involves the analysis of composite processing technology and advanced manufacturing cases. Specifically, we will examine the processing of film cooling holes in aircraft engine blades. As the heart of an aircraft, the performance of an aircraft engine directly affects the flight performance of the airplane. The processing of film cooling holes in blades is crucial for enhancing the efficiency and reliability of aircraft engines. We will delve into the composite processing technologies related to film cooling hole machining, exploring the underlying principles, methods, and their significance in practical applications. Additionally, we will also appreciate the significance of multi-technology integration for the development of national strategic industries. During the operation of an aircraft engine, the high-temperature gases inside exert a significant thermal load on the blades. To protect the blades, machining film cooling holes on their surface is a highly effective cooling method. When cooling air flows out through these film cooling holes, it forms an insulating air film on the blade surface, reducing the surface temperature of the blades. This, in turn, enhances the lifespan of the blades and the performance of the engine. Electrical discharge machining, EDM. Electrical discharge machining is a processing method that uses the high temperature generated by pulse discharges to erode metal materials. In the machining of film cooling holes in aircraft engine blades, EDM offers unique advantages. It can process various conductive materials without being limited by material hardness and is capable of producing very small holes. The basic principle is that when a pulse voltage is applied between the two electrode and the workpiece, an instantaneous high temperature is generated in the dielectric between the electrodes, causing the workpiece material to melt and vaporize, thereby being eroded away. After each pulse discharge, the dielectric between the electrode and the workpiece returns to an insulating state, preparing for the next discharge. In the process of EDM for film cooling holes, multiple factors need to be considered. These include pulse parameters such as pulse width, pulse interval, and peak current. The pulse width determines the energy of each discharge. The pulse interval affects the efficiency and stability of the machining process, and the peak current directly influences the rate of material erosion. In terms of formulas, the material erosion rate V is related to the pulse energy E and pulse frequency F. The pulse energy E can be expressed as E equals 1 divided by 2, Cu2, where C is the capacitance and U is the pulse voltage. The erosion rate V is approximately proportional to E times F. Here, the capacitance C and pulse voltage U determine the energy of each discharge, while the pulse frequency F represents the number of discharges per unit time. Laser machining. Laser machining is a processing method that uses a high energy density laser beam to melt and vaporize materials. In the machining of film cooling holes, laser machining can achieve high speed and high precision processing. The principle of laser machining is that the laser beam is focused on the surface of the workpiece, causing the material to rapidly absorb the laser energy. This results in a sharp increase in temperature reaching the material's melting and boiling points, thereby causing the material to melt and vaporize. Laser machining has the advantages of non-contact processing, faster processing speed, and the ability to machine complex shapes. In practical applications, laser machining of film cooling holes requires controlling laser parameters such as laser power, pulse width, and repetition frequency. Laser power determines the amount of energy used in processing. Pulse width affects the size of the heat-affected zone in the material, and the repetition frequency is related to processing efficiency. For example, for some specially shaped film cooling holes, such as inclined holes or irregularly shaped holes, laser machining can be achieved by adjusting the angle of the laser beam and the scanning path. A single machining method may have certain limitations, so in the processing of film cooling holes in aircraft engine blades, composite machining techniques are often used. For example, combining electrical discharge machining with laser machining. First, laser machining is used for rough machining to quickly remove most of the material and improve processing efficiency. Then, electrical discharge machining (EDM) is employed for finishing to ensure the dimensional accuracy and surface quality of the holes. This integrated approach of combining multiple technologies fully leverages the advantages of different machining methods, enhancing the quality and efficiency of film cooling hole processing. Taking a certain model of aircraft engine as an example, the processing requirements for its blade film cooling holes are very high. The hole diameter is usually between 0.25 and 0.6 mm, with some combustion chamber liners reaching up to 0.8 mm. The positional accuracy of the holes is required to be within plus or minus 0.05 mm. After EDM finishing, the surface roughness should be Ra is less than or equal to 0.8 μm. And after final laser finishing, Ra should be between 0.4 and 0.8 μm. Aerospace engines are a crucial component of a nation's strategic industries, and their manufacturing technology represents the high-end manufacturing capabilities of a country. The processing of blade film cooling holes, though seemingly minor, plays a critical role in the performance of aerospace engines. The application of multi-technology integrated composite machining techniques highlights the importance of system integration capabilities. As students of the new era, we bear the mission of building a technologically strong nation. Mastering system integration capabilities, organically combining different technologies, and applying them to actual production are crucial for advancing the country's manufacturing industry. We should take these advanced manufacturing cases as examples, strive to learn professional knowledge, and contribute our efforts to the nation's aerospace endeavors and the construction of a strong manufacturing country. In the machining of film cooling holes in aircraft engine blades, quality control is a critical aspect. The machining quality directly affects the cooling effectiveness of the film cooling holes and the service life of the blades. Dimensional accuracy control. Dimensional accuracy primarily includes the diameter, depth, and positional accuracy of the holes. The size of the diameter affects the flow rate of the cooling air. The depth is related to the effectiveness of film formation, and the positional accuracy determines whether the film can accurately cover the blade surface. To ensure dimensional accuracy, high-precision measuring equipment, such as a coordinate measuring machine (CMM), should be used during the machining process. Before machining, precise positioning and calibration of the tools and workpieces are necessary. During the machining process, it is important to monitor the machining parameters in real time and adjust the machining techniques promptly. For example, when the diameter deviation exceeds the allowable range, corrections can be made by adjusting the pulse parameters of electrical discharge machining (EDM) or the power of laser machining. Surface quality includes surface roughness and surface integrity. Surface roughness affects the formation and flow characteristics of the film, while surface integrity is related to the fatigue performance of the blades. To improve surface quality, appropriate machining processes and post-treatment methods can be employed. After electrical discharge machining, electrochemical polishing can be performed to remove discharge marks and microcracks on the surface, thereby reducing surface roughness. After laser machining, ultrasonic cleaning can be used to remove slag and impurities from the surface. To enhance the efficiency and quality of film cooling hole machining in aircraft engine blades, continuous optimization of the machining process is necessary. Process parameter optimization. The optimal machining process parameters can be determined through experimental and simulation methods. For instance, in electrical discharge machining, (SAW), the effects of different pulse parameters on machining efficiency and quality are studied to find the best combination of pulse width, pulse interval, and peak current. In laser machining, parameters such as laser power, pulse width, and repetition frequency are optimized to achieve the best machining results. A reasonable machining path can reduce machining time and tool wear. In multi-axis machining, by optimizing the tool's movement trajectory, the tool can quickly and accurately reach the machining position, avoiding unnecessary idle travel. Additionally, using a layered machining approach allows for the gradual completion of film cooling hole machining, thereby improving machining accuracy. With the continuous advancement of aerospace engine technology, the requirements for blade film cooling hole machining are also increasing. In the future, film cooling hole machining technology will develop towards higher precision, greater efficiency, and increased intelligence. High-precision machining. To further enhance engine performance, the dimensional and positional accuracy of film cooling holes will require even higher standards. The future goal is integrated control with sub-micron positional accuracy is less than or equal to plus or minus 1 μm and micron level diameter tolerance plus or minus 2 μm efficient machining. With the increasing demand for mass production of aerospace engines, improving the efficiency of film cooling hole machining becomes particularly important. The use of high-speed machining technology and multi-axis linkage machining technology can significantly reduce machining time, intelligent machining by utilizing artificial intelligence and big data technology. Real-time monitoring and automatic control of the machining process can be achieved. Through real-time adjustment and optimization of machining parameters, machining quality and stability can be improved. In this lesson, we focused on the machining of film cooling holes in aircraft engine blades. First, understanding the importance of film cooling hole machining for the cooling of aerospace engines. We then discussed in detail the application of composite machining technologies in film cooling hole processing, including the principles of electrical discharge machining, EDM, and laser machining, parameter control, and their combined application. We also examined real-world cases to see the effectiveness of these technologies in actual production. In terms of quality control, we emphasize the importance of dimensional accuracy and surface quality, as well as the corresponding control methods. We also discussed the direction of process optimization and the future development trends of film cooling hole machining technology. Through this study, we not only gained professional knowledge about the machining of film cooling holes in aircraft engine blades, but also deeply appreciated the significance of multi-technology integration for the development of national strategic industries. I hope everyone can remember the mission of strengthening the nation through science and technology and strive to enhance their system integration capabilities.